Homework 17, Chapter 5.4, Problems 2 and 6. A copper wire having a diameter is bent into a circle and held with the ends just touching. If it has a maximum permissible strain, what is the shortest length of wire that can be used? So, based on bending of a member, if you bend it about some location and the center of your member is rho distance away, then you're going to have a strain in your member proportional to the distance away from your center of your beam. And since our maximum will take place at the ends, we can use half of our diameter for our negative y value. We also need to find rho, which conveniently, due to how circles work, we can say 2 pi r, or 2 pi rho, is going to equal the circumference, or our length, and we can plug that into our equation, solve it for L, and get that our minimum length due to our maximum strain is 5¼ meters. Next, if we now have a given length, what is the maximum acceptable diameter of the wire if the maximum normal strain must remain below yield? Assume this given elasticity and yield strength. Now, we're not going to be using the E from part A since we're given it we're not going to be using the strain from part A because we're giving it elasticity and yield. And if we solve for our strain, and this right here, what I have is the exact same equation we solved for in part A, since that will be the relationship for this problem. But anyways, if we solve for the strain, then it's going to be sigma over E, and that's where we're going to be plugging in when we solve for our diameter. So we can plug in our values and get 4 millimeters. A bar of rectangular cross-section is loaded and supported as shown in the figure. The distance between the supports is L, and the height of the bar is H. Deflection at the midpoint is 2.5 millimeters. What is the maximum normal strain at the top and bottom of the bar? So, for a strain, again, we're going to be using the same equation that we're going to be using half of the distance from the center to the edge, which is h halves in this case, over rho. And if I were to draw kind of this imaginary rho here, having this here allows me to do some geometry. So I'm going to make it very big over here. Looking at this, I can say that if I take my p length and I subtract p cosine theta, that I will get delta, and my sine of my theta equals L halves over rho. Take a look at my image here and see if that makes sense to you. Once I figure this out, I can plug in my L halves over rho for my theta using the small angle approximation, which, even though it doesn't look very small on our image here, it is exaggerated. You can look at the numbers in the problem statement and it is a small amount. And due to the fact that there's a p in and out of the cosine, I can't solve for it numerically for p by itself, but I can use a calculator to find out my rho is 153 and we make meters. Then, since I'm solving for strain, I can plug that into my equation and get strain is 4.5 equal to 4. Next, part B reads, if allowable strain is 0.0006 and the deflection cannot exceed 4.2 millimeters, what is the maximum permissible length of the bar? So now we're going to be using the same equation that we had before that we solved for, except we want to find the length, and we have an epsilon given to us. So if I solve for my rho as a function of epsilon, because I can plug that back into the equation we created, then I can, this time I actually can algebraically solve for L because there's only one of them, and I can plug in all of the information and get that it is 2 meters. Alright, longitudinal strain. So this is the image I drew in the first problem, if we had some member that were bending, then the only way that it's able to continuously go in a circle is if we squish the inside part in through compression and have a tensile force pulling it out on the outer part. And this is where we get our strain from. And due to the fact that kappa and rho are inverse, you can write it as either way. However, for this class, we'll be using rho more because that's easier to solve for. And that's your equation. Hope this was helpful, and good luck on your homework.